And a lot of this is just to impress upon you how much science we do know about our climate system. The funny thing is, a lot of people say, I don't believe in climate change, because they may not know that there has been a lot of science done before they got there. It's like saying you don't believe in surgery. Like, you may not know the details, but it happens all the time. So let's talk about some of these things that we know about our world climate. In number 14, I have to just do a quick little distinction. In number 15, a little vocab, and then we'll get into climate with 16 and 17. Quickly, number 14, I'm going to assume you did the homework. We have to distinguish things living the atmosphere physically or things being removed from the atmosphere chemically. We have sedimentation, rain, oxidation, and flow dissociation. Which of those are physical movement of stuff out of the atmosphere? Sedimentation and rain, because that just moves stuff mechanically. You know, gravity and water falling. Which of them are chemical? Oxidation, photodissociation, and by the way, rain too. Rain is both physical and chemical. And the reason I mention this is most of you forget that rain will physically grab dust and pollen and whatnot. But rain is also reactive. Rain is water, and water mixes with oxides and other chemicals in the atmosphere to chemically remove things too. For example, rain can drop dust down to the earth. That's a physical movement of the dust. But rain can also remove carbon dioxide from the atmosphere by making it into carbonic acid. All rain is acidic. Yeah?
Well, the reading the reading makes sound like the oxidation makes, like it oxygen bonds and stuff, and it makes it like water soluble. Is that?
Yeah, right. So a lot of rain chemistry depends on oxygen reactions first. So things that oxidize, like we know, are now anoxides, and oxides plus water make acids. Water soluble will rain down. So water is both physical and chemical, and really depends on the other chemical reaction, which is oxidation. That makes sense to everybody in number 14? Oh, fine. Then let's talk about number 15 quickly. I don't know anything about sports, so I have to just go with my very, very limited understanding of sports. I have heard other people say that Kobe Bryant is a fairly exceptional basketball player. I don't really want to get into the debate about whether he is the greatest or just really good, but I think it is safe to say he's better than the average basketball player, right? Now, how do we determine that Kobe is better than average? Do we watch a single game, or do we develop averages from his entire career? Average from the second. It's possible that Kobe Bryant, who's a very good basketball player, might have an occasional off day and be way worse than average, right? I've even heard that Kobe's kind of famous for having amazingly bad days here and there. Climate and weather are the same way. Climate is the long-term average. Average of the whole planet, average over many, many, many years. There are what you might call exceptions to that rule. So even though the whole planet on average is heating, a couple spots might be cooling. And even though the long-term trend is heating, a couple of days might be colder than average. Don't confuse weather with climate. Regionally or short-term, anything is possible. The last ice age, there might have been a couple spots that were hotter. You know, globally the planet was covered with ice, but regionally a couple of spots may have gotten hotter. And we actually know that that was true. Today, despite the fact that the planet is getting hotter on average, some places are getting colder, like Europe. And within the long-term average, you may just get a couple of short-term flukes. The east coast of the United States is getting hotter the last 20 years, but last year was a really cold winter. You know, a little weather within the climate. A little variation within the long-term trends. Kobe is probably getting better at basketball, but he might have a worse than average game one of these days. I think we're all okay with that. I just get really irritated every time I go to the supermarket or every time I watch the news. There'll be some fool saying, there's no global climate change. It was really cold in my house this morning. It's like, well, regional and short term, but, you know, global and long term, we're definitely getting hotter. They're like, no, it snowed a lot in East Coast last night. Like, yeah, I know, but, you know, globally there's a lot hotter temperatures over the long term. Oh, no climate. I got sweaty yesterday. Okay. Please don't confuse weather with climate. It's one of my pet peeves. I think a lot of people don't realize that they're a different word, that they're a different concept. You guys may have heard that in Washington, D.C., there was an international convention of climate change scientists last year. And on Fox News, one of the announcers was like, climate change, it's a snowstorm, get it? And I was like, bro, climate weather. Mm-hmm. But like, people in public with big audiences make this confusing tangle. It's like saying, Kobe was the first story, probably a good basketball player. Yes. The long-term trends are really clear. And by the way, new research came out the day before yesterday in the journal Science. We have pretty compelling research that says the Earth for the last 11,000 years has been the general cooling trend. For the last 11,000 years, global temperature has been gradually dropping. You know, climate change is always gradual. So for 11,000 years, we've had a downward trend. And the last 100, we've had a steep upward trend. And the last 20, temperature has changed faster than in the known history of temperatures. As far as we can tell, the rate of warming on Earth the last 20 years is greater than any period of warming ever. The most rapid global warming ever believed to have occurred in the history of the Earth was that, about 250 million years ago. I believe it was a volcanic eruption that caused that. Volcanic eruption over here somewhere. No, sorry, excuse me. Siberia, over there somewhere. Somewhere over here. And when that Siberian volcano blew, it made a bunch of sulfur dioxide that caused really rapid global warming, that stopped currents, that changed global weather. That was the most rapid climate change ever, and it caused the most severe mass extinction event ever. We are changing temperature about 12 times faster than that.
Is the overall temperature of the Earth is the hottest it's been
in a pretty good while. Yeah, it's been much hotter in the distant past. But the funny thing is, the temperature doesn't matter. Like, everybody keeps talking about how many degrees, and that's the wrong question. It's how quickly. It's the derivative, right? It's not the change, it is the rate of change, which makes the big difference. And by the way, we notice what's called second derivative. We notice that the second derivative of temperature is also a positive number, meaning that the rate of temperature change is also increasing. Meaning not only is temperature going up quickly over time, but it's going up faster over a shorter period of time every year. Yes?
You said that like 12 times as fast. Are we also losing 12 times as many species?
Don't know yet. Lag time in ecological consequences. And also, we know that the net temperature gain of that was greater than our net gain now. So the rate of change makes this a deadlier mass extinction event, but the net scope of the extinction event remains to be seen because we don't know yet the absolute gain of our temperature gain. You know what I'm saying?
If we were to like stop it for the next couple of years, then it wouldn't really be anywhere near as fast as that, right?
It's an interesting question. Rate of change is greater, but the net change would be lesser. So what's better? 5 degrees over hundreds of years, or 2 degrees over a couple decades? It's an interesting question. We're not sure yet. By the way, we do know that if all humans disappear today, our global temperature will continue to rise for somewhere between 450 and 600 years at roughly the current rate. So it's very likely that even if humanity disappears overnight, which we're clearly not going to, because of these positive feedback loops, once you start the snowball, it'll still have this snowball effect, even without us. So it's very likely that no matter what we do, we will have a greater net change of temperature than compared to that volcano, and of course, it'll happen much more quickly too. So most scientists say that there's no way to avoid the greatest mass extinction events ever. We are the Holocene extinction because of our temperature change and the rate at which it changes. Okay. I can explain later how this was all figured out, by the way. We will talk about how we know the temperature hundreds of millions of years ago. But before we get into that, I want to talk about this dude, a Serbian named Milutin Milankovic. And Milutin Milankovic was a Siberian astronomer who in the 1940s, way before computers and satellites and fancy technology, using pretty old school telescopes and really, really sharp pencils and very good math skills, he ran a research project for many years trying to measure the irregularities of our solar system. I got to give you a concept that I'm guessing most of you can probably understand. When we taught you in what was it, the first grade about the planets? Kindergarten even? My daughter got into the solar system already, kindergarten? Whatever. When we taught you about the planets, we taught you circular orbits on a flat plane. Because it's a really easy way to get started. But just like we teach starting scientists about the atom, there are actually a lot of details about electrons, like us, a lot of details about planets. As it turns out, they're not all on one orbital plane. They have different planes. They're off kilter with each other. They don't go on the exact same flat orbital plane. Some of them have orbital planes that are kicked off the other planets. And second of all, their year is different. So 1 year from now, we'll will have made a lap around the sun, but other planets will still be a quarter of a lap. And so every now and then,